Welcome to another design video from the Ultralight Airplane Workshop. In this video we're going to talk about the wing geometry for the UWS-4 Ultralight Airplane. Now this is part 4 of a series. If this is the first video of the series that you've seen, I'll put a link up here in the upper right hand corner that you can go to, and that'll be a playlist for this series. So you can start part 1 and go on through it if you want to. Now this series is an attempt to carry out the procedures that we find in a book by Dan Raymer that's called Simplified Aircraft Design for Homebuilders. But in this case, we're applying it to an ultralight airplane. And we've reached part 4, and in part 4 we're going to figure out what the wing geometry is. In this case we're talking about things like span. We already know aspect ratio because that was figured out in part 2. We're going to figure out the surface area, we're going to figure out the chord at the root and the tip, the mean aerodynamic chord. And then we're going to have a little fun in a program called OpenVSP, and we're actually going to draw this wing in OpenVSP. Let's get started. Let's quickly review what we learned in the last episode, which was part 3 of the series. The first thing we figured out was our engine sizing, and we came up with 32 horsepower that we needed to take off at gross weight, but I happen to have a Rotax 377, which has a maximum of 35 horsepower, so that's what we're going to use. We also figured out the maximum propeller diameter we were going to have, and it turned out to be 5.26 feet. Now the way we came up with that is we figured out we want a maximum tip speed on a propeller to be 700 feet per second, and that's to help have reduced noise. I don't want to be annoying my neighbors while I'm taking off and landing. And that also helped determine that we're going to have a 3-bladed propeller because that also helps reduce noise. At least it's less noise than a 2-bladed propeller that has the same diameter. And by the way, if you haven't seen part 3, I'll put a link up here in the upper right hand corner that you can go to and review how he came up with these values. Now keep in mind that we are using Dan Raymer's book, Simplified Aircraft Design for Homebuilders, and what you're going to see in this video is not really a substitution for Dan's book. He puts a lot more information there that I'm going to cover. He has lots of tables and pictures and diagrams that are great to look at and give you a better understanding of the mechanics of what we're doing. And by the way, if you want to buy Dan's book, I'll put a link down in the description that goes to a page on the website, and down in that page, under Design Books or Design Resources, you'll find a bunch of links to Amazon where you can click on to go to buy the book. And just so you'll know, if you do use that link to buy the book, the channel will get a small cut of the proceeds. Let's quickly go over the items that we want to figure out or learn in this video. We want to come up with the wing area for our main wing. We want to have the span. We want to figure out the chord along the wing. So it's going to be the root chord and tip chord and the mean aerodynamic chord. And all of that actually comes from the plan form we want to use. So that's the shape of the wing as you're looking at it from the top. We want to figure out what dihedral we're going to have for our wing. We want to get a first estimate of what the size of our aileron is going to be. And that size is going to be some fraction of the wingspan and the wing chord. And then when we get all that done, let's just draw it up in OpenVSP and kind of get an idea of what it's going to look like. If you're following along in Dan's book, you'll want to go to page 24 because that's where he starts on figuring out the components and parameters for the wing configuration. Well, the wing area is really easy to figure out, and that's this symbol S here. What we'll do is take the gross takeoff weight, and we figured that out in part 2, and we divide that by the wing loading, and we figured that out in part 1. So from part 2, we figured out a gross takeoff weight of 517 pounds. From part 1, we figured out that our wing loading is going to be 3.9 pounds per square foot. So if you do that division, we end up with a wing area of 132.6 square feet. Now the FAA will let us make this wing surface area just a little bit smaller. And the reason we can do that is we can actually use a lower weight in our calculation. Now, why would we want to necessarily reduce this gross weight that we're using for our calculation? If we keep the same wing loading, then if we reduce this gross weight, we can reduce our surface area of our main wing. If we can reduce the surface area of our main wing, we can reduce the weight of that wing. A smaller wing will be lighter. And having a lighter wing will reduce the empty weight of our airplane. And if you'll remember, we want to make the empty weight of our wing be less than 254 pounds because of the FAA Part 103 regulations. And it's going to be hard enough to do that as it is. So if we can make our wing smaller, we need to do that. Now, if you remember up here, we used gross takeoff weight, and it included all kinds of stuff. It included baggage, It included a heavy pilot and just about anything else I could think of that I might want along on a flight where I'm going to fly to a neighbor's airfield to do some visiting and then fly back home. But in figuring out our gross weight in order to do this calculation here, we can actually leave some of that out. So, for example, instead of using a heavy pilot, where I use something like 190 to 200 pounds, the FAA will let us use a standard pilot weight of 170 pounds. We can also omit the baggage. Now, I had 15 pounds I used over in the Part 2 video. So if I used a standard pilot and no baggage, we actually come down to 472 pounds. So now if we stick that into our calculation, we come out with 121 square feet. And that's more like it. That's down close to the range that we want. We might be able to make it a little bit smaller once we select our airfoil, if the maximum coefficient lift of our wing would be more than 2, but for now, this will work. Well, now we have our surface area, let's go ahead and figure out the wingspan, and you'll find that on page 26 of Dan's book. So the equation for figuring out the wingspan comes from this. This is actually just a rearrangement of, let's go back to that title page, that's a rearrangement of this equation here, where you take the span squared and divide by the surface reference area of your wing, and that gives you the aspect ratio. Well, I turned all this around a little bit, so let's go back and look at that. So this is the same equation, just rearranged around, and this A is the same as the AR we just looked at. So we take our aspect ratio, multiply the wing surface area, and then take the square root of all that. That'll give us our span. Now, if you remember back in Part 2, we decided on an aspect ratio of 4.5. And also from that video, we know that lowering the aspect ratio lowers the weight of our wing. So I chose 4.5, and I'm still happy with that, so let's keep with that. So if we use our new wing area up here of 121 feet, and our aspect ratio of 4.5, and we plug all that in, we get a span of our wing of 23.34 feet. Now we're whipping through this wing configuration pretty fast. Next thing we're going to work out is the chords on various places on the wing, and that's still on page 26 of Dan's book. What do we want for our plan form? And in particular, the taper ratio. So we have a number of plan forms that we can select from. We have rectangular, that's often called the Hershey bar shape. We have tapered, where the chord is longer at the root and narrower out at the tip, and that could be like a linear shape. We have a semi-tapered, where we might be rectangular in a centered section and then tapered out on an outer panel. And we also have elliptical, where the entire shape of the wing is elliptical. And we can have variations on these. You could actually have a rectangular middle section and an elliptical outer section. Well, I want to use the rectangular plan form. And the reason for that is it's easier in construction. I can actually use one or possibly two templates to make all the ribs, instead of having, for example, a fully tapered wing, where I'd have to have a template to make each single rib going out there, so that adds a lot of time just making all those templates. Now, tapered can give you a slightly lighter wing than rectangular, but I don't think it's worth the extra effort, at least not for this ultralight we're doing now. So I'm going to stick with rectangular. Now that means our taper ratio is 1, because the root chord is going to be the same as the tip chord. And by the way, this lambda here represents the taper ratio. So let's calculate the chord then. It's really easy when our taper ratio is 1. We got a rectangular wing. So this is the equation if you have some taper, and with this just being 1, this becomes 1 plus 1, which is 2, which actually is canceled out by this 2 up here, which means all we need is the surface area of the wing divided by the span. And that gives us chord of 5.186 feet, so roughly 62 inches. Let's go ahead and mention sweep really quickly. Keep in mind that the sweep of the wing is the angle between the 25% chord of the wing and a line parallel to the y-axis of the wing. Since we have a rectangular wing, our sweep is 0 degrees. So this is lambda also. This is a capital lambda. I should have mentioned before. Back here, this lambda, that's the taper ratio. This is a lowercase Greek letter lambda. And the rectangular sweep is an uppercase lambda. So that's 0 degrees for that, since we're using a rectangular wing. The reason we have a sweep of 0 is I don't see any advantage of having a sweep here on this ultralight airplane. There could be possibilities when you might need a little forward sweep or a little backward sweep. So the only reason I think of for an ultralight is if, for example, you might want to give it a little forward sweep. If you have the pilot pretty far in front of the CG and you'd like to get a little bit better visibility up, you could certainly do that. Or if you're doing a flying wing, of course, in that case, you'd have some backward sweep. Now, the next thing to talk about would be the mean aerodynamic chord. And if you got a taper to your wing, this would be the equation that we'd use to calculate your mean aerodynamic chord. And by the way, if you don't know what mean aerodynamic chord is, I'll put a link up here in the upper right hand corner that is linked to a composite terminology video that I did sometimes back that'll help you figure out what mean aerodynamic chord is. But we have a rectangular wing, which means our mean aerodynamic chord is the same as our root chord and our tip chord. So we don't even have to go through this equation, which is really nice. Well, next thing we're going to work on is dihedral. Now, he gives different amounts of dihedral depending on whether you're swept or unswept or low wing or high wing. I haven't really talked about it before, but I'm thinking of doing a low wing on this airplane. And the reason for that is it makes it much easier to have a really wide stance on the landing gear because I'll put the landing gear underneath the wings out about 4 feet or so from the center. So that'll give me a nice wide stance. Now, of course, you could put landing gear underneath the high wing. There are a number of large airplanes that do that, but I don't want to do that. It makes the landing gear really long, which adds a little bit of weight. It's also difficult to make it strong enough. So putting a low wing with a shorter landing gear saves us some weight and makes the landing gear fairly sturdy. So Raymer recommends then a dihedral between 5 and 7 degrees. Now I'm going to pick 5 degrees. I don't mind at all being at the lower end of having lateral stability, which is what dihedral is supposed to give you. It's supposed to give you lateral stability. In other words, rolling left and right. So I think 5 degrees will be fine. So the next thing we're going to figure out is the size of our ailerons, and that's on page 31 of Dan's book. Now, if you remember, back in episode 1, when we were figuring out our coefficient of lift, we used 2.0 because the FAA Advisory Circular 103-7 lets us do that in Appendix 2. But in order to do that, we have to have our flaps over 50%. Whatever portion of the wingspan then that isn't taken up by flaps or the fuselage or nacelles, that portion that's left over we will assign to ailerons. Now, how much of that it's going to be is really up to us. So 25% would be a fairly good value. 33% would be a fairly good value. What I'm going to do then, since I'd like to have reasonably responsive ailerons, is I'm going to try a flap span of 66%. That would leave 33% for the aileron span. So let's try that to start with. I think that's going to work out reasonably well. Now you notice that I actually didn't leave anything for fuselage or nacelles. What I'll do is, if I have to have some nacelles or fuselage take up part of the span, I'll start taking off from the aileron until it gets down to about 25% of the span. And once it reaches that, then I'll start taking off from the flaps. I don't want my ailerons to be any less than 25% of the span. And of course, I don't want my flaps to be any less than 50% of the span. Now, Dan has a nifty little table in there then that says if you know what the span of your aileron is going to be, he'll help you figure out, using that table, what the chord of your aileron should be. Now, from Dan's table, we can see that for that 33% span aileron, then the chord could be anywhere from 25% of the chord of the wing to 36% the chord of the wing. I'm going to pick 25% of the chord. Ailerons that get over 25% are a little bit draggy, and you're going to have a lot more issues with adverse yaw when you're using them. So I don't really want to get any more than 25%. All right, let's go over real quick what we've learned here. We came up with a wing surface area of 121 feet. We come up with a span of 23.3 feet. We decided on a rectangular planform. The chord for the whole wing is 5.186 feet. We don't have any sweep. Of course, I mean aerodynamic chord is the same as our wing chord. And we're going to pick a dihedral of 5%. Now, I'd like to see what this is going to look like. So let's go into OpenVSP and draw this out. I'm in OpenVSP now, so let's make that wing. Let's start with the default wing that OpenVSP will make for us. We come up underneath this list, come down to Wing, select Add. So you can see it added a wing for us. Let's go change the name of it real quick. And let's just change it from Wing Geometry to Wing. Now you can see the default wing here. Let's remove the sweep first. So you come up underneath Section. Now we only have one section in this wing so far. Let's go down here under sweep. And right now it's at 30. Let's change it to 0. The sweep location at the moment is along the leading edge. Now it really doesn't matter where we set the sweep location to since we're going to be a rectangle. But we said we do it 25% of the chord, so let's go ahead and add this in here. So now the sweep is at 25% of the chord is 0. Let's go ahead and set our span. Now I've already copied it from the slides we just did. So let's come up under span and let's do a paste. Control V. So it's 23.34 feet. Let's go ahead and set the taper to 1. That'll take care of that little issue. So now the taper is the same at both the root and the tip. Now let's go get our tip chord. So that is 5.186 feet. Copy that. And we'll paste it down here. Now I just realized I made a little bit of a mistake here. On this section, on span, it's actually a semi-span, so it wants to know from the root out to the tip. So what I need to do is divide this by 2. So I'll put a /2 in here and hit a return. Now that looks better. The way I knew that is I realized the aspect ratio was too long. So this aspect ratio looks right. It's about a 4.5. And to verify that, let's come up underneath plan and then come down to this aspect ratio, and it is 4.5. So right on the money. Next thing to do is set the dihedral. So let's do a view from the front. Okay, let's go back to our section. Come down to the dihedral section. And let's put 5 in here. So because we want 5 degrees of dihedral. Okay, that looks about right. Now, last thing to do is put our flaps and ailerons in here. So let's get a top view again. Come up to view, hit top. Let's squish it down a little bit. Now, in order to put an aileron in here, we need to put a subsurface in. We come up here to sub. We select control surface. We have surface 0. That's the only surface we have so far. We hit add. So here's the control surface so far. One thing I want to do is get rid of this little section in here. You can see that there's some lines down here on the root. I don't want that. So let's come back up to plan. And then for the root cap, I'm going to say none. So that gets rid of that. Now you can see it actually moved our surface here. Now there's a little something funny about doing surfaces. When you go into location, you don't actually put like feet in here. You actually put percentage of a section. Now, if I had left the root in here, we would actually have 3 sections that this aileron could go over. One would be the root surface, one would be the top surface, and then one would be the end surface. Now, I got rid of the root surface, so now we only have 2. We have this flat surface, and we have the end surface. That means that our aileron locations start at 0 here at the root. It goes to 1/2 here at the edge, and then it goes to 1 out on the end surface. So it's a little bit strange, but it'll work. So let's come back over to sub. So we're going to do the span, and at the start location is going to be 0. So let's put 0 in here. We said for the flaps, let's go ahead and say these are flaps. In fact, just to make it a little easier, let's put this in here. So now we have flap for the name. We want this flap to end at 66% of this semi-span. But we know that its location, its U location, goes from 0 to 1/2. Well, we can actually cheat a little bit. We can actually say, let's say that 1/2 is all the way over, and then multiply that by 0.66. That should put it exactly where we want. So there we are at 66% of the semi-span. So that worked perfectly. Now let's do the ailerons similarly. Let's do another add of a control surface. Let's change that to aileron. So now you can see it just shoves some values in here. We want to start where we finished off the ailerons. Eventually we won't put a gap in, but for now we'll start the exact same spot. So let's again do that 0.5 times 0.66. And then for the end, like I said, up here is 1/2. So let's go ahead and put 0.5 in there. So it ends right at the end here. Now this wing isn't done yet by a long shot. There are more things I want to do. I'm going to want to put my own kind of tip on here. And what I'll probably do, let me look at the front again. What I will probably do in the future, before too long, is I'm going to put a flat center section in here, because that'll let me have slightly shorter landing legs. So I'm going to put the landing legs out here on the wing. That'll mean I'll have two sections in here, which means I'm going to have to redo my flaps and ailerons, because that'll give me three surfaces that these ailerons and flaps will be on, so I'll have to recompute all that. And let's take a little better look at it by turning the shading on, and let's get rid of the boxes. So there you can see what it looks like. Of course, another thing we're going to have to do in the next video is select the airfoil that we're going to use for this wing. So, like I said, the next video will be about selecting the airfoil for the UWS-4. I want to take a moment to thank my patrons. At the designer level, we have Keith, Richard, and Shane. And at the early bird level, we have Ryan. Thanks for supporting the channel, guys. You rock. If you haven't gone over to Facebook yet and done a like on the UWS Facebook page, there's a link down in the description that you can click on and it'll take you right to that page. Now, if you like this video, make sure you give it a thumbs up so YouTube will think other people might like it too and recommend it. Okay, guys, thanks for watching. Until next time.